Welcome back to the deep dive. Today, we're doing a really focused exploration of Azure storage.
Yeah,
And not just recalling features, we're going to be analyzing these architectural scenarios where, common sense can sometimes lead you down the wrong path.
that's right. The goal here is to get beyond just memorizing what a feature does and really distill the foundational knowledge you need for actual architectural reasoning.
Right.
We're looking at those tricky situations, the nuances that trip people up when they're designing something complex, or frankly, when they're studying for something like the AZ-104 exam.
And our source material for this it's basically a deeply analytical scenario pack. It's all about the interplay between the key storage components,
Hmm.
the exact spots where your intuition might say one thing, but Azure's implementation demands something else entirely. We've structured this around, I think, 4 core themes.
Yeah, we've got durability and cost,
Yeah.
then networking, then access control and security.
And finally, choosing the right service for the job.
So let's unpack this. We're going to dig into these scenarios and really make these foundational choices stick by looking at what happens when you get them wrong.
Okay, let's start with the absolute fundamentals.
Wow.
How your choices on resilience, on speed, and on data location just immediately shape your architecture and, well, your budget.
Always the budget.
We're kicking off with a classic conflict. Compliance versus convenience. So imagine you're working on a financial application.
Okay.
It needs to be super durable, survive local hardware failures, regional resilience is key. But here's the twist. There are strict compliance rules that say the data can never leave the original geographic region.
This is a great one because the mistake here is so common. People automatically equate durability with, spreading data as far as possible.
Right. You hear high durability and you immediately jump to GRS.
Geo-redundant storage.
Of course.
It sounds like the best.
Yeah.
I mean, it replicates your data 3 times locally and 3 times to a completely different region hundreds of miles away.
So for pure disaster recovery, GRS, or its even better cousin, GZRS, Geozone Redundant Storage, that seems like the top choice.
It would be. But in this scenario, the moment that data packet leaves the primary region, you've violated the compliance mandate. So GRS and GZRS they're off the table immediately.
So that's the first rule of architecture then. Compliance beats technical preference.
Every single time. If the rule says no cross-region replication, you have to find the best possible option that keeps the data local. You're looking for maximum protection, but within that regional boundary.
So what does that leave us with? What's in the redundancy matrix that gives us that high durability without crossing the border, so to speak?
The correct solution here is ZRS, Zone Redundant Storage. But, and this is a big but, only if the Azure region you're in actually supports availability zones.
Okay, so let's quickly review the baselines just to put that in context. LRS is the cheapest.
Right. LRS, locally redundant storage, gives you 3 copies of your data, but they're all inside a single data center. If that specific building has a major failure, you could lose everything.
And ZRS improves on that how?
ZRS takes those 3 copies and it spreads them out across separate, physically isolated data centers, the availability zones, all within the same region.
So they have their own power, cooling, networking, all that.
Exactly. So this gives you that intra-region resilience. You're protected against a full data center going down, and you get that 11.9's durability target, all without breaking that compliance rule about data leaving the geography.
That is the critical distinction. You are protected from a data center failure, but you're not protected from, say, a massive earthquake that takes out the entire region.
That's the trade-off. Absolutely. You gain compliance, but you lose that ability to just instantly fail over to a secondary region if there's a huge regional disaster.
Which really ties into those architectural concepts of RTO and RPO, your recovery time and recovery point objectives.
It does. With GRS, your RPO would be lower, meaning less data loss, and your RTO would be better because that secondary region is already hot and ready to go. With ZRS, if the whole region is gone, well, your RTO for getting back online somewhere else is going to be much, much longer.
So the key takeaway here, especially for any kind of architectural exam question, is if the requirement explicitly says no cross-region replication, the answer has to be ZRS.
It's a hard boundary. And the follow-up trap is if later on that same application needs geo-redundancy and zone resilience, that's when you'd look at GZRS, but only if that compliance rule gets relaxed. Always solve for the problem in front of you.
Okay, shifting gears now to security fundamentals. We've got a scenario where a new compliance team is, going through their Azure checklist. They're trying to manually enable encryption settings because they think it's a required step.
Yes. This is a classic case of bringing old assumptions into a new environment. The wrong assumption is that encryption at rest is something you have to, like, flip a switch to turn on.
So what's the core fact that every single Azure admin needs to just burn into their brain about this?
The core fact is that Azure Storage encryption at rest is on by default. It's not optional, just part of the service.
So every storage account is encrypted.
Every single one. It uses 256-bit AES encryption. It happens automatically. It's totally transparent. And you don't have to do a single thing to meet a basic compliance rule for encryption at rest.
So if I see an exam answer that proposes a solution to turn on encryption, I know it's wrong because you can't turn on something that's already on.
Exactly. That is guaranteed trap. The real conversation isn't if the data is encrypted, but who holds the key.
And that's the architectural nuance. So when does manual configuration actually come into play?
It's only necessary when your compliance rule is more specific, when it demands customer-managed keys, or CMK. If your organization's policy says Microsoft can't hold the encryption keys, then you have to get involved.
And that's where you integrate with Azure Key Vault.
Precisely. And when you do that, you aren't turning on encryption. You're just telling Azure, hey, instead of using your own key, use my key from my vault to wrap the key that actually encrypts the data.
So you're just changing the key source, the key manager.
It's all about control and auditability, not about the encryption itself. So if a scenario just says data must be encrypted at rest, the answer is probably no action required. If it says customer must control the keys, then the answer is Key Vault integration for CMK.
Okay, let's move on to performance, a much more tangible problem. Here's the situation. A new high transaction workload, maybe it's a real-time ledger or something, is seeing really high unpredictable latency, and we find out it's running on a GPv2 storage account with standard HDD storage.
This is a mistake we see all the time. Admins assume standard storage is good enough for most things because, it's the default and it's cheap.
And for some things, like backups, it is, but not for this.
Not for high transaction workloads, no. For something that's doing lots of small concurrent reads and writes, standard HDD is almost always going to be your bottleneck.
Why is that? What's the inherent limitation?
Well, standard storage is built on spinning hard drives, HDDs. And even in the cloud, that means higher latency and, more importantly, much lower and often unpredictable IOPS input-output operations per second.
And there are account-level caps on that, right?
Exactly. You hit that ceiling on throughput or IOPS, and your application just grinds to a halt.
So if the problem is explicitly about latency or IOPS, what's the immediate non-negotiable solution?
The solution is to upgrade the storage account to the premium tier. It's that simple. Premium is backed by solid-state drives, SSDs, and it's designed specifically for these high IOPS workloads.
So lower, more consistent latency and much higher predictable throughput.
Yes. So when you see a performance problem, the first thing to check is the SKU, standard versus premium.
That's a critical distinction, but we all know premium costs more. A lot more. What if the budget is tight and we can't afford to put all, say, 500 terabytes of data on premium?
Now that is a real-world architectural problem. If budget is the main constraint, you have to get smarter. You implement a data management strategy.
Okay.
You put only the most actively used data, the hot path, that drives the application on premium storage. Everything else, like logs older than a month, backups, analytical data that can go in standard cool or even archive tiers.
Which requires really clear data segregation.
And careful container design, yes.
Yeah.
But it's how you balance performance and cost.
So we've established performance is about the SKU, but maintaining that balance over time, that brings us to cost optimization.
Right.
In this scenario, we have a company generating tons of log data. The container is getting really expensive because all the logs, even ones that are years old, are just sitting in the hot tier. So the IT team tries to fix it by setting the storage account's default access tier to cool, but the bill doesn't really change.
And they've fallen right into the trap. They're relying on the default access tier setting to manage ongoing costs, and it just doesn't work that way.
So the default tier, hot, cool, or archive, only affects a file when it's first uploaded.
Only on initial upload. It does nothing to manage the data state after that. So if you upload a file to a hot tier and then change the account's default to cool, that original file stays hot. The expense clock just keeps ticking.
So to actually move data around based on its age or how often it's accessed, you need automation.
You do. The correct solution here is to configure lifecycle management rules.
Okay, tell us how those work.
They're basically powerful little rule sets that run in the background. You can define conditions, usually based on, days since last modification or access, and then trigger actions.
So you could say something like, if a blob in my logs container hasn't been touched in 30 days, move it to cool.
Exactly. And if it hasn't been touched in 180 days, move it to archive. After 2 years, just delete it. It's set forget cost optimization.
This really hammers home a critical point. The default access tier is for initial placement. The lifecycle policy is for ongoing automated transitions.
Yes. And a quick architectural reminder about that archive tier. It is dirt cheap, but there's a big trade-off.
Access time.
Access time. You can't access data directly from archive. You have to initiate a restore operation, a rehydration, which can take hours. So if you need to access the data even occasionally, cool is a better fit. The big takeaway is that moving data from hot to cool or archive requires a lifecycle policy. You can't do it just by changing a default setting.
Okay, so we've covered data placement and cost. Now let's move into networking, which is, I think, where some of the most complex traps in Azure storage really live.
Oh, definitely.
This is all about balancing security with accessibility, especially for services inside a virtual network. Here's a tricky one. An admin wants to lock down a storage account, so they set the firewall to the most restrictive setting, deny public access. They have VMs in a VNet that are using service endpoints, and they just assume this will work, but then suddenly the VMs lose all access.
This is a textbook misunderstanding of how service endpoints actually function. The common mistake is assuming that a service endpoint is like a true private connection that just automatically bypasses the firewall.
But service endpoints do keep the traffic on the Azure backbone, right? They identify it as coming from a VNet.
They absolutely do. A service endpoint is a network optimization. It tags the traffic leaving your subnet with the source VNet and subnet ID. So the traffic never goes over the public internet. But that tag does not equal a firewall bypass.
So if public access is denied, the firewall still checks the request, it sees the tag, but it still needs a specific rule to let it through.
Precisely. The core fact is this. Even with a service endpoint, if the default action is deny, you must go into the storage firewall settings and explicitly allow the specific subnet ID where those VMs live. If you forget that step, the firewall just blocks it.
The service endpoint is working, but the firewall config is what's blocking you.
Yes, the firewall configuration is paramount.
And this really highlights the key difference between service endpoints and private endpoints.
It does. Private endpoints are what you want for true zero trust, or when managing all those subnet rules just gets too complicated.
So what's the fundamental difference in how they work?
A service endpoint, as we said, relies on public IP routing with internal tags and firewall rules. A private endpoint is the truly private solution. It actually injects a network interface card for the storage account directly into your VNet's private IP space.
So the traffic never even tries to go to a public endpoint, it's all local?
It's fundamentally local traffic, so it bypasses the public firewall entirely. The takeaway is, service endpoints need firewall configuration. Private endpoints bring the storage account into your private network.
Okay, so now let's talk more about that superior option, private endpoints. Because even when you deploy them correctly, they often fail to connect. In this scenario, a VM has a private endpoint setup, but it can't connect because its request resolves to the storage account's public IP address.
The infamous DNS problem. The mistake here is thinking that Azure just magically handles all the DNS overrides for you when you create a private endpoint.
But the magic doesn't happen automatically. Private endpoints depend entirely on what to redirect the traffic.
They depend 100% on DNS resolution. When your VM tries to access, say, mystorage.blob.core.windows.net, something has to tell it to go to the private IP in your VNet instead of the public IP on the internet.
And what's the piece of Azure infrastructure that does that internal mapping?
You have to configure and link a private DNS zone. For blob storage, the zone has to be named exactly right, something like privatelink.blob.core.windows.net.
Okay.
That zone contains the A record that maps the public name to the private IP. And crucially, you have to then link that zone to the virtual networks where your clients are.
So if that zone is missing or it's not linked, the client just does a normal public DNS lookup, tries to hit the public IP, and the firewall, which is correctly configured to deny public access, just blocks it.
Correct. The private endpoint is just sitting there in your VNet, completely invisible because nothing is directing traffic to it. And this gets even more complex when you bring in hybrid networks.
Right. If you have people on premises trying to access that private endpoint over a VPN or express route, their on-prem DNS servers have no idea what a private link zone is.
Exactly. So you have to set up DNS forwarding. You configure your on-premise DNS service to conditionally forward any requests for those private link zones over to the Azure DNS servers. Without that forwarding, your on-prem users are just going to try the public path and get denied.
It's a multi-layered DNS configuration that really makes or breaks the whole architecture.
It really is.
Okay, let's move into access control. Azure gives us a ton of tools keys, SAS tokens, RBAC, ACLs, but the tricky part is understanding the scope. Knowing when a credential manages the resource versus when it manages the actual data.
This is a huge one.
Here's a very common mistake. A developer needs simple read-only access to some blobs in a container to, I don't know, debug a config file. An admin, trying to be quick, just gives them the contributor role on the whole resource group.
Oh, no.
Now the developer can delete the entire storage account. A massive over-permission.
This scenario is the perfect illustration of the confusion between Azure's two control planes. The mistake is using resource group RBAC to control access to the data inside the account.
So let's define those two planes. What does resource group RBAC actually control?
It controls the management plane. This is all about operations on the resource itself. Things like creating or deleting the storage account, changing its redundancy from ZRS to GRS, configuring the firewall. The contributor role is super powerful on this plane.
It lets you destroy the resource.
Yes. So if the developer just needs to read a file, they need access to the data, not the infrastructure. So how do we grant access to the actual content?
That's the data plane.
Exactly. And to control that, you need to use specific data plane RBAC roles, like storage blob data reader or storage blob data contributor. These roles give granular access to the actual content, and you can scope them right down to a single container.
So the right solution is to apply the blob data reader role just on that one container, least privilege.
That separation is a critical architectural guardrail. And what's interesting is that the contributor role at the RG level has zero inherent permission to read or write the data inside the containers.
Right.
Not unless you also give them a data role. The takeaway is RBAC does not control access to the data plane. And this is also why account access keys are so dangerous. They give you full control over both planes for the entire account simultaneously. They should only ever be used by trusted applications, never people.
Okay, let's talk about another high-stakes security problem, SAS tokens. A developer needs to share a huge log file with an external partner, fast. So they generate a full control shared access signature token for the container, make it valid for 24 hours, and email it.
I can see where this is going.
5 minutes later, they realize what a terrible idea that was. They've given away the keys to the kingdom for a whole day. They need to revoke that one specific token right now.
And the common wrong assumption is that you can could just go in and instantly revoke one specific ad hoc SAS token.
But you can't. Why not?
Because a simple ad hoc SAS token is basically a cryptographic promise signed with the storage account keys. Once it's out there, Azure doesn't keep like a list of all active ad hoc tokens to check against.
So how do we handle this immediate crisis? There's a 24-hour full control token out in the wild.
You have two options, and they're both pretty broad. If it's a critical threat, you have to use the nuclear option. Regenerate the storage account key that was used to sign it.
And that breaks everything.
It breaks every single SAS token that was issued using that key. It'll probably cause application outages, but it guarantees that rogue token is immediately useless.
That seems like a really destructive fix for a single token problem. What's the better, more architecturally sound solution?
The better long-term fix, the one that gives you granular control, is to tie the SAS token to a stored access policy.
Okay, what's that?
A stored access policy is something you define directly on the container. It's like a template that sets the permissions and the expiry time. Then when you create the SAS token, you just reference that policy.
So if I create a policy called external access and then link a SAS token to it, if that token gets compromised, I can just delete the policy.
You just delete or modify the external access policy, and every single token associated with it becomes invalid instantly. It gives you that immediate granular control that ad hoc tokens just don't have.
So the lesson is, if you have to use SAS, bind it to a policy.
Yes, though ideally, you should push for identity-based access with Azure AD RBAC whenever possible. But if you must use SAS, remember that trap. Ad hoc SAS tokens are non-revocable unless they're bound to a stored access policy.
Okay, we've spent a lot of time on securing and managing the account. Let's move inside the account now and look at the different services, blobs, files, queues, and make sure we're picking the right one for the right workload.
This is critical.
So here's a classic lift and shift problem. A legacy app moving from on-prem expects a traditional SMB file share. The workload is lots of small files, high I/O, frequent metadata operations. The migration team, looking at the costs, suggests using blob storage with, say, the SFTP protocol as a substitute.
A purely price-driven decision that completely ignores the workload semantics. A very common mistake. The wrong assumption is that because blob storage can store files, it can act like a file share.
What's the critical piece of functionality that the legacy app needs that blob storage just fundamentally can't provide?
It needs the semantics of a shared file system. Blob storage is object storage. It's completely different. The correct solution here is Azure Files, and probably the premium tier if that low latency and high I/O is important.
Why will the app just break on blob storage?
Because blob storage doesn't do things like NTFS semantics, file locking, the kind of concurrent access handling, or the rapid directory operations that an application mounted on a Windows server expects. Blobs are just immutable objects.
So if the application code is written to use Windows file paths, file locks, NTFS permissions, it's just going to fail.
Immediately and constantly. Azure Files is purpose-built to be a fully managed cloud SMB share. It supports everything that app needs. The distinction is crystal clear. If the workload acts like a network drive, you need Azure Files. If it's just storing objects like backups or media, you use blob storage.
Sticking with Azure Files, let's look at an authentication challenge. The requirement is to mount Azure Files shares using existing on-premises Active Directory credentials.
This tests your knowledge of hybrid identity. The mistake people make is assuming Azure Files only works with Entra ID because, that's the cloud native direction.
But Azure Files is explicitly designed for these hybrid scenarios, right?
It is. The core fact is that Azure Files supports two different methods for domain-based authentication. It supports Entra ID Domain Services, which is the managed domain controller service in Azure, and it supports direct integration with your on-premises ADDS.
So to meet that requirement, using existing on-prem AD accounts, what's the architectural step?
You have to enable the ADDS authentication feature on the storage account itself. This basically makes the storage account act like a domain-joined computer object. It needs line of sight to your on-prem domain controllers.
And once that's set up?
Once it's configured, your users can authenticate against their on-prem domain when they map the Azure file share, and you manage all the access control using standard NTFS permissions, ACLs, right on the files and folders, just like you always have.
That makes it a really powerful tool for those slow, phased migrations to the cloud.
It does. The key takeaway is that Azure Files is versatile. It supports both Entra ADDS and on-prem ADDS. So if a scenario specifies on-prem AD credentials, that is a perfectly valid and supported solution.
All right, let's talk about scaling and service limits. A company needs to deploy hundreds of independent application environments. The team decides the best way to get strict isolation is to just deploy thousands of tiny, separate storage accounts. They very quickly hit a subscription level limit and everything stops.
This is a classic case of confusing physical separation with logical segmentation. The assumption is that you need a unique storage account for every single isolated workload.
But there's a hard limit.
There's a hard limit. It's high, usually 250 or 500 per subscription, but it's not infinite. Trying to create thousands of micro accounts is just not a scalable or efficient design.
So what's the correct, scalable way to get that isolation without hitting those limits?
The correct solution is to consolidate. You use fewer, larger storage accounts, and you use containers or file shares as your unit of segmentation. Then you apply granular access controls at that level.
So you use the tools we've already talked about, RBAC, ACLs, private endpoints, to create logical walls inside a single account instead of building physical walls with separate accounts.
Exactly. You might have one big storage account called production web assets, and inside you have containers for app A, app B, and so on. Then you use blob data RBAC roles to make sure app A's identity can only touch the app A container.
So the architectural lesson is that segmentation does not require creating tons of storage accounts.
Not at all. Use containers and identity-based controls.
Okay, let's shift to data protection features inside blob storage. A developer accidentally overwrites a critical config blob. Maybe they upload an old broken version of an XML file. The team's first reaction is to start a restore from their traditional external backup system.
That is the common wrong assumption. And while backups are absolutely essential for disaster recovery, they are total overkill and way too slow for recovering one accidentally overwritten file. Your RTO would be terrible.
So what are the two built-in features that give you near instant recovery for these kinds of mistakes?
The correct solution is to make sure you have both soft delete and blob versioning enabled. Soft delete is your safety net for accidental deletions. It just keeps the file around for a while so you can undelete it.
And versioning is the feature that solves our specific scenario, the accidental overwrite.
Correct. When versioning is on, anytime a blob is modified, Azure automatically phases the previous state as a distinct recoverable version. So in this case, the developer could just instantly roll back to the version from moments before the bad overwrite. Recovery is immediate, and all happens inside the storage account.
The architectural nuance here, though, is cost. Keeping all those versions and soft-deleted items takes up space.
It does. Versioning will increase your storage consumption. So architects need to monitor that and usually combine it with a lifecycle management rule to automatically clean up old versions after, say, 90 days. But the key takeaway is that backups are not required to restore an overwritten blob. Versioning gives you that capability instantly.
All right, let's look at asynchronous communication. We have a simple job scheduler that's using Azure Queue Storage, but it's occasionally losing messages or processing jobs twice, especially during high-volume periods.
The mistake here is thinking that queue storage is a one-size-fits-all solution for any messaging workload. It's designed for massive scale, simplicity, and low cost. But it's built on an eventually consistent architecture. It just lacks enterprise-grade guarantees.
So if the application needs higher durability, guaranteed delivery, duplicate detection, or message ordering, what's the right service?
The correct solution is to switch to Azure Service Bus. Let's talk about why. Queue storage is very simple. Your application has to do all the hard work, retries, poison message handling, all of it. If your app pulls a message and then crashes before it's done, that message can reappear later, leading to duplicates or even loss if your code isn't perfect.
And what does Service Bus provide that solves those problems out of the box?
Service Bus offers things like sessions, which guarantee message ordering critical for financial transactions, for example. More importantly, it has a built-in dead letter queue, or DLQ. If a message fails processing over and over, Service Bus automatically moves it to the DLQ. This isolates the problem message without losing it and lets the main queue keep flowing.
So Service Bus is the transactional enterprise-grade choice, while queue storage is for simple, high-volume scenarios where you're willing to write all that resiliency logic yourself.
That's the perfect architectural dividing line. For mission-critical workloads that need guarantees, you have to use Service Bus. The exam trap is clear. Use Service Bus for enterprise workloads and queue storage for simple, high-volume, eventually consistent jobs.
Okay, here's a web hosting scenario. A team is hosting a simple static site using the static website feature in blob storage. They're ready to go live, but they can't figure out how to implement their custom domain name and, critically, get a managed HTTPS certificate.
The trap here is assuming the static website feature is an all-in-one solution that handles custom domains and TLS out of the box. It's a fantastic, cheap way to serve content, but it's designed to be the origin, not the entire delivery pipeline.
So if the requirements are a custom domain and HTTPS, what's the mandatory architectural layer you have to add on top?
The correct solution is to use the static website feature combined with either Azure Front Door or Azure CDN. You put your HTML, CSS, and images in blob storage, and then you layer Front Door or CDN in front of it.
And why are those services mandatory for a professional setup?
Because blob static hosting can't do custom TLS termination. Front Door and CDN are global services that provide that. They handle the custom domain mapping, they provide free managed HTTPS certificates that auto-renew, and they cache your content at edge nodes all over the world for faster load times.
So you just point the CDN or Front Door origin to the static website's endpoint.
Exactly. The static site feature serves the content, but you need a global delivery service on top for a production environment. If the scenario demands a custom domain in HTTPS, the answer must include Front Door or CDN.
All right, our final distinction. This one is about scale and I/O patterns. A user is trying to upload a single massive video file over 200 gigabytes, and the upload just fails because it's too big for a standard single upload.
This really tests the foundational understanding of the different blob types. The mistake is confusing the roles of page blobs and block blobs, or thinking you can just push a file that big in one go.
We have two main blob types. Which one is designed for massive sequential data, like big files or backups?
That would be the block blob. Block blobs are optimized for huge sequential uploads. And for a file this large, you have to use a technique called chunking. You break the file up into manageable blocks, you upload all those blocks, and then you send one final command to commit them into a single cohesive file.
And that's how you can get a single blob up to, what, over 190 terabytes?
That's right. So for a 200 gigabyte video file, block blob with chunking is the answer.
So what is the very specific limited use case for the other type, page blobs?
Page blobs are designed for workloads that need frequent random write operations. They're structured as a collection of 512 byte pages, so you can read or write specific byte ranges very quickly. Their number one most famous use case is being the backing storage for Azure virtual machine disks.
So that's the clear association. VM disk equals page blob.
VM disk, think page blob. Huge sequential file stream, think block blob with chunking. The architectural choice is completely dictated by the I/O pattern.
That is a very clear trap to remember.
It is. VM disks are page blobs, general file storage, huge objects. That's all block blobs.
Wow, we have really dissected this scenario pack. We've gone from high-level compliance rules with ZRS all the way down to the nitty-gritty of block versus page blobs.
We really covered the 4 crucial areas for your Azure Storage Foundation. We hit ZRS for compliance, the absolute need for private DNS zones with private endpoints, that hard line between the management plane and the data plane for RBAC, and the critical need to use Azure files for any SMB workload.
And the whole mission here was to make these distinctions memorable, to help you reason through these complex designs and, well, avoid those technical traps that always seem to show up. I think you should now have a much clearer mental framework for these decisions.
And if we connect all this back to the bigger picture, to long-term architectural planning, it raises a really interesting forward-thinking question for you to consider.
Okay.
When you're designing a storage architecture based on today's needs, how do you decide if strictly prioritizing a current requirement, like using ZRS for compliance, is worth sacrificing future strategic flexibility, like the ability to move to GZRS for zero downtime regional failover before your application is even scaled to that critical level?
That's a great question. It's that constant tension between solving for today's hard constraints and planning for tomorrow's potential.
Exactly.
A perfect thought to end on, always prompting us to look 2 steps ahead. Thank you for diving deep with us today.